7e. A particle moves along a straight path through a displacement vector of d. Now this d vector is in 2 dimensions. 8 meters I hat plus c meters j hat, while force F is equal to 2 newtons I hat minus 4 newtons j hat. All right. So I always like to visualize this because you know all these numbers, they all look fine and all, but I just like to visualize it a little bit better. So what do? I draw. So here, my force. I'm going to use my force in aquamarine blue, and that looks like 2. So 1, 2, and then 4 in the negative, right? So this would be the force vector. So here's the force vector. And then, if we were to take a look at the displacement vector, now the displacement vector, we really don't know, but we only know it's going to be 8 this way, but we don't know whether it's going to be up c or down c, right? So we need to figure that out. Other forces act on the particle, which is valued at work c if the work done F of the particle is 0. Excuse me. All right. So c vector, the c component of the displacement vector d, we don't know yet. Okay? So let's figure out what's going on when these 3 different things are happening. Okay? All right. So let's see. When it is equal to 0, I should use different color. This work is equal to, right, F dot D, okay? Now the force, we know it as 2 I hat minus 4 j hat, right, newtons. And we're going to dot that with 8 I hat plus c j hat meters. Okay? So if we were to put these 2 together, when we dot it, we get 2 times 8, right, plus negative 4 times c. So that's what work is right here, right? Well, if we were to look at this 2 and 8, they're in the same direction, right? So the angle between that is 0 degrees. So this one, you could say cosine of 0 degrees. Okay, so since this is plus, this will come out to be plus. So cosine of 0 degrees is what we have here. Here, it looks like because of this negative, right, this looks like cosine of 180. Okay, so for part A, right, if work is equal to 0, right, then since this is 8 times 2 is 16, plus negative 16. So this has to be negative 16 right here, right? So C has to be positive 4. Right? I guess J hat if you want to say it, right? So C is equal to positive 4 meters. Okay, so I guess it's going to be something like one of these Johns, right, for part A. Okay. So this would be like 8, 8, 4, right? What about for part B? For part B, if you want it to be positive, that means this displacement vector has to be somewhere less than 90 degrees, because this is 90 degrees right here for part A. So if this is true, then in order to be positive, this angle has to be less than 90 degrees to be positive. Therefore, your C value has to be less than 4. Okay? It has to be less than 4. So if work is positive, right, then C has to be definitely less than 4 meters. And for part C, if work is negative, right, that means my C value has to be bigger than 4, so it has to be, this angle has to be greater than 90, because this has to be pointing that way, right? So then C has to be greater than 4 meters. Okay? Is that okay with everybody? All right. Alrighty then. Let's move on to the next page. All right, here in figure 7-26, a cord runs around two massless frictionless pulleys. So these are massless and frictionless pulleys. Right? A canister with mass of 20 kilogram hangs from one pulley. Okay, so this is 20 kilograms. And you exert a force on the free end of the cord. So you're applying a force here. Okay. What must be the magnitude of force if you are lifting the canister at constant speed? So my net force is 0. So this thing's going to be going with no acceleration at all. Okay. So if I were to take a look at this scenario right here, what is the tension on these cords? Like, well, it's a one cord, but there are two tensions happening, right? So let's see. If I were to draw a free body diagram, I see like tension here. Let's see. Tension here. Right? And I definitely see the gravity working on this thing, mg, down here, pulling down, right? So this is Fg, which is equal to m times g, right? So if we were to look at this, right, these two tensions plus the FG going down has to equal to 0 because constant speed, right? Sum of all forces is equal to MA in the y direction, right? In the y direction. And the sum of all forces in the y direction is equal to, looks like I got two tensions, right? Plus FG, right? So MAY is equal to, now two tensions, I'm going to keep that positive. And then FG, I'm going to make that negative because it's pointing down. But you know, acceleration has to be 0 because it's going at a constant speed, right? Therefore, my tension is equal to 1/2 Fg, right? So tension is equal to 1/2 mg. Okay? So what is my tension? Right? So my tension is equal to 1/2 times 20 times 9.8. So my tension is equal to 98 newtons. Right? All right. What about part B? To lift the canister, okay, by 2 centimeters, how far must you pull the free end of the cord? Well, if you were to pull this thing up, you need to actually lift this thing 2 centimeters. Then the both side of this rope has to lift 2 centimeters. So more likely, it's going to have to travel 2 centimeters down and 2 centimeters up. So 4 centimeters has to be moved completely, right? 2 centimeters up here, 2 centimeters up. So to do that, this thing has to travel 4 centimeters in order to lift this 2 centimeters up. I hope that made sense, okay? Because if I were to say, okay, let's just draw a little picture here. If I were to lift 2 centimeters, right? This point has to travel to down here, right? And this point has to travel, so this thing has to travel this plus that, right? So in order to go 2 centimeters up, this has to travel 4 centimeters to travel 2 centimeters up. Okay, so I'm going to say 4 centimeters, right, total, right, because right, you need 2 centimeters from both sides. Right? Okay. All right, then how about part C? Part C asks, During that lift, what is the work done on the canister by you? Well, if you're raising this thing by, you're actually working 4 centimeters of distance that you travel, right? Even though this thing only goes up 2 centimeters, you are still applying, right, 4 centimeters worth of distance for the force that you're applying here. But what is this force right here? This force that you have to apply has to be same as the tension going up, right? So this tension and this force has to be the same value, okay? So I'm going to say the force dot delta y is what we have, okay? So the force is really the same as the tension, which is 98 times 0.04 meters, right? And that is, what is that, John? So 98 times 0.04, and I get, oops, sorry, 98 times 0.04, I get 3.92 joules, right? And that looks like how much work you need to do in order to raise that thing, right, 2 centimeters. Now, if you want to work it the other way, so if you want to say how much work is done by tension, right, you could simply say 2 times the tension dot delta y. But this time, 2 times 98 times, but delta y for the tension is only 2 centimeters, right? So if you think about it, that's exactly the same thing as this, which is 3.92 joules. And they're both positives, okay? So even though this thing has weight of 196 newtons, because of this pulley right here, you are having a mechanical advantage, okay? Doesn't mean that you're getting more energy out of it. It just means you use less force, but longer distance, right, to do the same amount of work, basically. So this is called mechanical advantage, not energy gained. Okay. All right. So maybe you could write that down, actually. So because you're only using, right, so only pulling with half the weight force. Right? That is mechanical advantage. Okay. All right. Okay. So even though we're getting same amount of work done, here I only use half the weight of the thing, but I have to travel twice as far, right? So same amount of work done. All right, what about part D? The weight of the canister. Well, the weight of the canister here is going to be Fg, right, dot delta y. Now, I forgot to mention the direction of this, right? So for force, right, we're going to actually be pulling it down, right? And delta y that we travel is pulling it down, so it's going to be right? The distance traveled is going to be 4 centimeters down, and force is going to be pointing down, right? For tension, it's going to be pulling up, and delta y is pulling up, right? So the angles between them are 0 degrees for both. Here, my FG is down, but my delta y is up. Okay? So for this, I have 196 times 0.02 times cosine of 180 degrees. Okay? So this one comes out to negative 3.92 joules. So work done by gravity is negative work done. Okay? Any questions so far? All right, good, good. All right, let's take a look at the next one. Draw a force diagram. All right, so worker pushes 27 kilogram block, 9.2 meters along the level floor at a constant speed again, with force directed 32 degrees below the horizontal. If the coefficient of kinetic friction is 0.2, how much work did the worker do on the block? Well, the force applied for the worker is down 32 degrees down the right horizontal, right? So this is 32 degrees. So this is the force push by the worker. Now, we're going to have Fg, right? Fg, and we shall also have normal force. And notice I drew the F normal a lot bigger than my Fg. You'll see why later. And here I have a friction and I have, I guess you could say F push X, which is F push times cosine of 32, and you have F push Y, which is F push times sine of negative 32 degrees, right? Negative. You could put negative 32 in here, it'll still come out to be positive value, so that doesn't really matter. Okay? All right? So what's going on? Well, let's think about, if this has to be constant, right? So sum of all forces in the x direction has to equal to 0, right? So let's say sum of all forces is equal to, in the x direction, is max, but sum of all forces in the x direction, I have F push X plus friction, right? Therefore, max is equal to F push x, I'm going to keep that positive, minus friction. We know acceleration is 0 because it's moving at a constant speed. Therefore, F push x happens to be F push times cosine of, I guess, negative 32 degrees minus, right, mu times the F normal. All right, well, but what is this F normal, John? If we know that, then we could calculate the F push, right? And once we calculate the F push, we have to just do the dot product of F push and delta x, then boom, we're done. All right? So let's look for F normal so we could figure out what F push is. So if you could say sum of all forces in the y direction is equal to MAY, and sum of all forces in the y direction is equal to, it looks like I have F normal plus FG plus F push y, right? So when I set these equal to each other, MAY is equal to F normal minus MG minus, right, F push y. Yeah, don't put negative 32 in here if you want to do this, because I already gave direction here. So just figure out what the magnitude of this is rather than putting in 32, rather than putting negative 32. Because if I put negative 32, this will come out to be negative. The negative of the negative will be just positive, so don't do that. So just figure out the magnitude of this, because I already gave direction. So here, I'm going to be 0. So maybe for this one, I'm going to just put 32 degrees rather than negative 32. And I'll do the same here. So since F normal is positive, I'm going to bring both of these negatives to the other side. And let's solve for what F normal is, right? So F normal minus mg, which is like 27 times 9.8, minus F push times sine of 32 degrees. Okay, so I'm putting a positive 32 in here because I already gave negative sine. All right. All right, then what is that, John? So what's 27 times 9.8? Looks like I got 264.6. So my F normal is equal to, right, 264.6 plus sine of 32, I get 0.53 F push. Okay. So I have this and I could substitute that in here. Okay, because I have this. So my 0 is equal to, what's cosine of 32? It's like 0.848, right? So 0.848 F push minus mu, which is 0.20 times F normal, which is 264.6 plus 0.53 5, 3, F push. Ugh. Algebra. It's all algebra from here. Come on, right? So where are we? Let's just work it out then. Right? If you work it out, here 0 is equal to 0.848 F push minus, right, what is 264.6 times 0.2? I get 52.92 minus 0.2 times 0.53. I get 0.106 FP. Okay. So I can solve this now, right? So 52.92 is equal to, right? So 0.742 FP. So my FP is equal to, right, 71.3 newtons. Well, now that I found my FP, I can find work done now, finally, right? So work is equal to FP dot D, right? So we can say my work is equal to FP, which is 71.3 newtons, times D, which is 9.2 meters, times cosine of the angle between D and F push is 32 degrees. Not negative 32, just 32, right? Therefore, if we work this thing out, I think you'll get, let's see, 0.3 times 9.2 times cosine of 32, right? And I get 556.4 joules. All right. Any questions? All right. Good. Then maybe we have time for one more. When we have variable force, right, or varying force, non-constant force here. So 13. A 5 kilogram block moves in a straight line on a horizontal frictionless surface under the influence of force that varies with position as shown. Okay? How much work is done by the work as the block moves from the origin to 8 meters. So this is my delta x, or my position axis, and this is my force axis, and here's the zero force. Okay, that's the zero force. So how much work is done? So graphical integration basically means area, right, bounded by, right, function and a horizontal, right, the f equals 0 line. So if you really want to, you could have put the x-axis here, I guess, right? So you need to find, area between here. So this is work 1, let's say, right? And then you could say this is like work 2, right? And then this looks like 0 right here, right here. And then you need to find work 3. And this horizontal line right here, I'm going to label it with green so that we can see that green is the horizontal line. Okay? So, well, what is work 1? Work 1 is equal to 2 times 10, or 10 times 2, which is 20, right? And it looks like it's positive because this is positive 10 newtons. Right? What about work 2? Work 2 looks like 1/2 times, right? I guess 10 times 2, right? And that looks like 10 joules. And again, it's positive, right? 1/2 base times height. And then work 3 looks like 1/2, right? Looks like -5 times 2, right? Therefore, it looks like -5 joules. So, how much work is done? Well, work net is equal to basically work 1 plus work 2 plus work 3. Right? So my work net is equal to 20 plus 10 plus -5. So it looks like work net is equal to positive 25 joules. All right. Any questions? All righty. All righty. Again, I will have these posted on Schoology if you want to take a look at it again. I will put this PDF format as well as the video of this. Okay. Looks like we got a minute left. I guess I'll stop here. If you want, again, this looks like an area underneath this line. Okay, you could estimate that. Okay, and if you know the actual function, you can always do the integration. Okay. All right. Any questions? I think I'll stop here. I think it's good enough. All right.